Hi, my name is Vinay, and today I would be demonstrating software named as MentorDSP. So when you start up the software, this is how it looks like. MentorDSP is very easy to use with a very short learning curve, a DSP learning software package. So it is being designed keeping in mind for the engineering students who, when they are in second year or their third year of engineering, and they want to quickly understand the DSP concepts in a very easy to go manner, they can make use of the software to understand all the concepts of theory and perform some practicals also over here. So MentorDSP has tried to cover most of the concept from the DSP books, like sampling theorem, the effect of ADC-DC resolutions, what is aliasing, what do you mean by data coding, and energy power concept, speech formats, probability densities. Then from the transform side, we have tried to cover Fourier transforms in an overview manner, where you can learn about Fourier transform, what is inverse Fourier transform, and what is the use of Fourier transform for real-time spectrogram or the windowing concepts. It also has some convolution theorems like basic convolution principles and how these principles are applied in correlation and signal extraction from the noises. Apart from that, it also has concepts of filters like FIR filters and IR filters. So you can design some FIR and IR filters and see the effect of them on some signals. Okay. Apart from that, it also has some modulation concepts like amplitude modulation, frequency modulation, and then some digital modulations like QPSK, GMSK, CDMA, and OFDM. It also has some techniques from image processing, like studying the image properties, the operations which you can perform on images, then some transform on the image like DCT, which is used for image compression, then some image correlation, noise, and filtering also. So in a short overview, it covers most of the concepts. So I just give you a quick demonstration of MentorDSP, that what kind of experiments and how you can make use of it. So for example, on the first lectures, you are teaching your students that, okay, what is signal looks like a sinusoidal waveform. So this is how the GUI of MentorDSP looks like when you are working on the waveforms. So it is split into two parts. One is the top window and the bottom window, or you can say up and down window. So on the up side, you can see a sinusoidal waveform, and on the bottom side, you can see that it is showing the frequency domain or the Fourier transform of the same signal. So on the right hand side, you can see the properties like value, average value, energy, power, period, frequency of the signal, etc. from here. And also some other buttons for navigation, zooming, and capturing, and the playing of the sound. I will let you know one by one. So on the top side, you have like signal generator. So for example, from here, you can generate various kind of signals, like right from basic signals like sine, cos, clock, triangle, etc. But you can also generate like amplitude modulation, frequency modulated signal, or a chirp signal, FSK signal, and PSK signal, ASK, QPSK, CAM, CDMA, OFDM. So there are a lot many number, DTMF signals, or even if you are not happy with it, you can write the equations and ask him to generate the signals. So like this is sine 2 pi will look like. So if I ask him to add something like 1000, okay, so this is how the signal will look like. And if the same, I make it 200, so this is how the signal will look like. Okay, so you can even write the equation of your own and generate a signal. And even though if you're not happy, you can apply an input waveform file or an audio input clip, and you can plot the signal and process it further. Okay, we come back to our experiment. Okay, so for example, I just asked him to generate an 800 signal. Okay, so this is how it will look like. So you can just go to time scale and you can spread it so that if you want to see it more clearly, this is how it will look like. So on the bottom side, you can see that it shows an 800 hertz peak. So that is nothing but the frequency domain. So you can explain to your students that a sinusoidal is a pure tone. It has only one frequency attached to it. So if you give it 800, you should see an 800 peak. It is 797 because this is how the Fourier transform works, because he converts a time domain signal into a frequency domain signal using some mathematical computation. So these are the minor errors which are produced by the computation. So instead of 800, it shows you around 797. But if you increase the number of points you take for your frequency conversion, for example, instead of 512 points, I take 1024 points. So I should find it more accurate. Okay, so 797 is quite close. Okay, so if I change this signal to maybe 750, so I see an 754 hertz signal. If I change the points to 512 points, so you can see that the peak shifts a little bit. So slightly some more errors on noises are being added, but I think that we can manage. Okay, so you can go to up window and broaden this signal, and this is how it look like. Now maybe on the day one, many of the students may understand, many may require some more concepts. So you can quickly ask them, okay, that this is the 750 or something. So I go to equation, I write over here only 750, okay, and remove the second part and generate over here. So you see the same signal. So on the top side you see a sine wave which is compressed right now. I mean, it's zoomed in. And on the frequency transform you see a 754 signal. Now if I ask him that, okay, what will happen if I add two sine waves? Okay, oh, maybe yes, sorry, before doing that I just go to back, select the bottom screen also in time domain, so that the students cannot see what is happening in the frequency domain. Maybe I just broaden this and ask my students that, okay, what do you see in this signal? Is this good signal or bad signal? Maybe few students may say that this is a very bad signal, because the signal they cannot identify the signal, because they see some signals going up and down and they are not able to make any sense of it. So that's why you tell them that this is how the Fourier transform helps us to understand, because in Fourier transform you see the frequency domain that clearly there are only two peaks of 150 and 750. So that means there are only two sine waves present in the input with a frequency of 150 Hertz and 750 Hertz. That's it. There is no noise present in it. Okay. The same way you ask them that, okay, again go to back signal generator and maybe add another third signal, which might be somewhere around maybe 450. Makes it much more smoother, maybe 400. I just wanted to make it a little disturbing so that students cannot understand what is happening. Yeah, 1200 looks good. Now maybe I just show this signal to students and ask them, okay, what do you see now, this signal? So they might again say that this is a very dirty signal having a lot of noises. They can't see any stable signal, whereas this is the cleanest signal as possible, because if you see in the Fourier transform, you see only three peaks coming out, 150, 750 and 1200. So that means there are only three sine waves present in the input with these frequencies. Okay, so this is the cleanest signal possible. But now if you add something like a Gaussian noise with a high amplitude, okay, and generate it, so now you can see that yes, this signal, okay, if you see in time domain, this is how it will look like. Okay, and if you see in the Fourier transform and a little bit lift the level, so you can see that yes, there are three peaks of 150, 750 and 1200, but at the same time you see a lot of other peaks coming in. So these are nothing but the noises because these are unwanted signals present in the signal. Now you can even play the signals. So you can click on play 1 or play 2. As of now both signals are same, so that's how we hear them. And if you just remove the noise, so you won't hear the hissing sound, so you hear a very clear tone. Yeah. Then you can apply the same stuff concept to real-time spectrogram to make make students understand how the Fourier transform can help in identification. So as of now, you can see the Mentor-DSP showing you the time domain representation of the microphone input. So as I speak, you can see the microphone is responding on the top side. So I can just click on the one and maybe just reduce the amplitude so that we can, oh, hello, 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 aloha. Yeah. So you can see the signals are coming up. And on the bottom side, it shows real-time spectrogram. So he's plotting all the magnitude of the frequency on this spectrogram. So on the x-axis, you have the time scale, and on the y-axis, you have the frequency. And the magnitude of the frequency or the signal is represented with the color. So blue being the lowest intensity and white being the highest intensity. So as of now it is very sensitive, so we can reduce some intensity on the frequency range. So let's just reduce this. Okay, this looks better. Yeah. So I just clear it. So as I speak, you can see that the signals are plotted on the spectrogram. So maybe we can ask students that, okay, how the frequency lines can be represented. So we can make them practice how various tones and sounds produce what kind of frequency spectrum, because that will help them to design some applications regarding that. Okay. So here we are. So let me show some frequency over here. For example, whistle. So when I whistle, you can see some lines coming over there. So I just stop it so that we don't miss the signal. So you can remove this button and capture microphone. So here you can see that when I was whistling, you saw a straight line of almost 1200 or maybe 1100 something kilohertz, hertz. And so when I was whistling, I was able to maintain my sinusoidal frequency to the same line. Okay. And although there were some noises present, that's why you see some other lines coming up. These are the noises of the other frequency. The same stuff can be shown in the Fourier transform first. So if I go to Fourier transform, you can see here, okay, so in this you have to go reverse. Yeah. So you select the Fourier transform and now whistle. So you can see I'm able to whistle at a center frequency of around 1000 Hertz. And let me try to shift my frequency. So you can see this is how the peaks kind of came, right? I can whistle from 1000 Hertz to around 1600 or maybe 1800 Hertz. So that's quite a wide range. And same can be displayed in the spectrogram. So here you can see that I whistle from 1000 Hertz to almost 2000 Hertz. So that is the working of it. Now maybe you can ask students that how you can design a frequency operated door lock. So this is what they can design, because every human being has a very natural whistling tones and frequency. If I'm able to whistle at, let's say, 1060 Hertz, so there would be very few people who can maintain that frequency for a longer duration. So everyone has a different tone. So you could design with a sharp cutoff of 1060 Hertz and notch filter, and then you can only allow that frequency to pass through the filter. And when you have that frequency for more than 1 second, or maybe let's say 5 seconds, the lock will be opened. So these are very simple designs can be made. So the application will come to the students. if they are very clear about the concepts of the DSP. So this was the introduction of the Mentor-DSP. To start with, that how it can make use of it. So you can cover like various concepts like sampling theorem. Okay, so for example, I just take an input signal instead of 100, maybe maybe 400 hertz. Yeah. So this is my input on the top and this is my output at the bottom. So I can ask him to sample the above signal and show me result. Now, as per this Nyquist criteria, my sampling frequency should be more than twice of the input bandwidth. So if my input signal is 400, my sampling should be more than 800. So I'm sampling at around 11 kilohertz. So that's good. So you can see the output produces very nice. So if I drop down to 5 kilohertz, the output is still recognizable as sine wave, but it has some ladders coming up. That is of the sampling. This is at 2.7 kilohertz. Now this is at 1300 kilohertz. Now according to Nyquist, I am more than twice the input bandwidth, but my output signal, you can see that it is unrecognizable and I cannot identify what it is. But then the point is, I'm using my eyes to do that, which is not good because I have to use my mind to find out what is inside the signal. So you can see that the students might get confused and they can see that yes, this is not a good signal and probably the Nyquist criteria is not working properly, which is not true. We can go back to the sampling theorem and reset to 11 kilohertz and go back to Fourier transform now and see what is happening over here. So we see that the Fourier transform shows a single peak of around 400 hertz in this window. We can just move the scale to 1000, okay, 5000 scale. And now we do the sampling. So when we sample at 11 kilohertz, things look good. Now I sample at 5 kilohertz. Okay, I just increase this. Now I sample at 5.5 kilohertz. Now I sample at 2.7 kilohertz. So all of a sudden you see that two peaks coming in. Now as you lower down the frequency of your sampling, there will be more noise added to your signal. So as the noises are added, your signal distorts. Okay, so this is what is happening. Now the output is shown with addition of 400 plus this maybe 24 something hertz and this maybe 3200 hertz. So all these three are added and then shown to the output. Now when I go to 1300 kilohertz of sampling, okay, which is more than Nyquist, and then you see there are more sine waves coming in and they are all added and they distort the signal. But all I can remove this after using an FIR filter or low pass filter of the input bandwidth. If my maximum input of the signal is 400 hertz, I will, after the sampling, I will pass through a low pass filter of 400 hertz. So obviously all these high frequency noises will be removed and my signal would be smoothened out. I will have only sine wave present at the output or the input which is lower than 400 hertz bandwidth. So this is all going smooth till now. But if I go lower than the sampling frequency, which is 400, and now I'm sampling at something like 689, or maybe I just try to set it with exactly this. So now you see and noise is added also at 400 hertz. So this also can be removed with a low pass filter. But if I sample at maybe 700, so now you can see that this is my 400 hertz signal and another noise is added at around 350 or something, and this will be inside my signal bandwidth. So by no method I can remove this noise. Okay, this I cannot remove this numerical error noise. So this will be passed to the output and then I cannot detect what was inside my input signal because this will always distort the signal. So hence your sampling frequency should be more than twice of the input signal bandwidth. Then only you can remove all the noises and errors, etc. Practically, obviously, your sampling frequency should be more than 10 times of the input bandwidth. This is my practical experience. That's what I do. Okay. So this was a sampling. The same way you can illustrate the effect of resolution of the ADC-DAC. For example, any signal, you take it and you decode in 16-bit and you do it in 2-bit. So what happens? So you can see that you have ladders and steps coming in, but as the more and more resolution of the ADC or DAC, things get better. So this is a 4-bit resolution and it's 16-bit resolution, and it smooths out quite good. You can always play the signals and see the effect of it. So I can play 2-bit, so you can hear the sound difference. So this is the input is pure tone and the output is a little distorted. And same way you can do the data coding. So this is about illustrating the effect of fixed point and floating point numbers. So you have any number like 0.123. So you want to represent in fixed point numbers using only 4 bits. So how it would be represented? Okay, or maybe 8-bit. So it will be not 1, 2, 3, it will be 1, 2, 1. Whereas if you use in floating point precision format, so that will be very accurate and closest to the value. Okay. Furthermore, MentorDSP has concepts of Fourier transforms, so you can introduce your students about Fourier transforms, inverse Fourier transform, that how the coefficients of cosine and sine wave, when added together, they can create any signals you desire for. So for example, a full sine wave is a single, okay, I have to add F50. So if you just modify one coefficient of the sine wave, how it will look like. So this will be, that is the one frequency, that is the second frequency, and the frequencies are also listed on the bottom side. And if you add another coefficient, so what will happen? So it will produce a different kind of signal. And if you keep on adding those coefficients of cosine, okay, so this is how the kind of produce it can bring. I just say and select, and you can make anything of your choice. For example, triangle wave. So what coefficients are added, you can see from the drop down, and you can see the numbers coming up or coefficient values. You can also see for this ramp waves. So this is how it is. You can see the coefficients coming up. Okay, and there you are. Then you can see the square wave. Okay, so for square wave, more the number of coefficients, better the squarish shape is. As of now, you can see a little bit rise and fall time coming up. So that is because the number of coefficients are limited over here, around 7 each. So, but if you keep on increasing the number of coefficients, this will become sharper and sharper. Okay. Oh, yeah, not playing this is not. So all Fourier transforms. The convolution principles that also can be explained to the students over here. So on the right hand side, you see the convolution result or the output. On the left hand side, you can produce a signal of your choice from the signal generator. For example, this is an impulse generated on both sides, and the second window is being shifted. Okay, so as of now, you can see that as you shift this signal, okay, so where you find the maximum correlation result is the point at which both of the signals are coinciding to each other. Okay, so this will produce a maximum convolution result. So at this point, the user can understand that yes, both signals are aligning to each other. And if you shift it, you can see the convolution goes down. Okay, so if you take some more other signal, maybe a step signal, yeah, so that also you can do. So this is step signal, and you can just scroll and so fit in the window. Yeah, as of now, the convolution result is almost to 0, but if you just shift it, so you will find that it will reach to its maximum value when both of the signals are coinciding to each other. So probably it is at 5 milliseconds. So at that point, both the signals are coinciding to each other. So that is at 200 hertz. So that is what this offset is. Okay. So you can take various kind of signals and do this convolution exercise with the students. And they are other like extracting signal from the noise, Okay, for example, this is sinusoidal waveform is generated of 250 hertz, and a white noise is also added. Now you can see the amplitude of the sine wave is very low, it's around 0.2, and the noise is 1. So that's a very strong signal. Okay, that's a very strong signal. And if you just shift it to maximum 1, yes, now you can see that this is autocorrelation with averaging. So you can see the sine wave is being extracted, although a little bit of noisy, much better than what we are expecting on the input side. So this was a nice signal, and this is the extracted signal. So this can be again further filtered to produce the desired signal. The same is with filtering. So the users can generate various kind of filters, for example FIR filters. Yeah, so as of now this signal on the first window is 10 Hz to 5 kHz a signal, and we can play this to remember the sound. So you can see that a ramping kind of signal. So you can see there's a spectrogram. Okay, so we'll just reduce this. So you can see that the signal varies from 10 Hz to 5 kHz and moves down in the same linear fashion. Okay, moves up. So now if we perform this frequency FIR filter, okay, so you can remember the sound. So you can see the sound intensity is the same throughout. So we say that, okay, make a low pass filter, or maybe let's say cut off at 900 Hz. And let's say the order is only maybe 4, not much, and you can see show the inverse Fourier transform and make it casual. You can apply the window as you like rectangular, Hamming, and Blackman. So I just apply rectangular. You ask him to generate and FI filter coefficients. So he will show you the coefficient required for making this filter, and you just say compute. And over here you can see set it to view all. Now if we play the second signal, so you can hear that this is very it gets faint after a while. So where the input signal is same as throughout, there is second, which is the output one, it gets faint after a while. Okay, and maybe I go to synthesis, and instead of this make it 20, or maybe just 25. And again apply window, and this time also we compute. Now this time you can see again the coefficients coming up. Okay, you can see all the coefficients. You can use it, export to Excel file, and do as you like with them. So now this time you can see that attenuation is very sharp and the ripples are very low, and the follow through. So you can hear the sound that after a sound it suddenly becomes faint. This is the input which is having a strong sound throughout. This guy faints after a while. You can see that effect also coming up in the spectrogram. Okay, I have to use this too. So I have to reduce the magnitude of the frequency range. Due to recording, it's refreshing a lot. Okay. So now you can see that after a while, it starts well with the red zone, but after a while it gets green and it gets faint and nothing comes up. So that means there is no frequency present after the desired one, that is 900. They might be ripple after a while, but they also decay very soon. So this was FIR. You can export these coefficients from the export tab to MATLAB or in an Excel file or to Scilab, or even for our hardware kit, where you can download these coefficients into a FIR filter and see the same experiment working in the hardware. The same is for IR, only the synthesis method is a little different. Okay, and the cutoffs etc. are much more sharper. So you have to just say okay 998. You can just select the quality factor and the bandwidth of the quality factor and compute. So you can see that image is much more sharper. It has a little decaying, and that's okay. So IR filter is also present. The same way the synthesis also has other concepts, like you can talk to students about discrete system, effect of them, and making your own discrete system. For example, this is echo generation. Now in this case, what we do is we just go to up and say view all this has it loaded on. Okay, I just go to signal generator. So from this audio section, we can just load any audio signal. So I just go to the installed folder and look for sounds folder, and there I can find a lot of sound samples. So for example, I just select this A alphabetical vowel generator. So we can clearly hear these vowels. So just we play one. A, I, U, E, O. So these are all English vowels. Now we just generate this echo of the same sound. So this is the echo generator. So you can see that the output is being fed back to the input with a delay of 1000 samples. So you can see that just 0.5 multiplied by a previous sample with 1000 ones, delayed one. Okay, and the input is also being fed back to the input with a delay of 1000. Okay, so you just say click on update coefficients and compute. So you can see that this is the vowel but with the echo effect. So we just play 1 and 2 and see the effect of it. A, I, U, E, O. Now the echo one. A, I, U, E, O. A, I, U, E, O. So you can hear a little bit of echo coming up from the sound. So this is how the echo generation works. So you can see that the coefficients generated and the comparison done for the delays. So you will find that you have to see the thousands one. Okay, that's a bit quite long. Then you also have the concepts of modulations, like amplitude modulation. You can make use of it, and frequency modulation. You can just update the frequency coefficient and see the effect of it. And modulations like QPSK. So you can see the transmitted data, what's the modulations frequency. So instead of 900 megahertz, we work at 900 hertz. So the concept remains the same, only the understanding has to be made. Okay. Then other modulation like CDMA, you can see the carrier digital data with the code and the modulation frequency, and you can even add the noises to the channel. And at the receiver side, you have to just multiply with the code and the cosine to get back the signal. So all these concepts can be illustrated using for the modulation also. We also we have this image basic modulations and transform techniques. So for example, you can just load this image. So we went into sound, this time into images, and load any image like okay basic camel. So if you click on any pixel, it will show the red, green, blue combination of the colors, and it will show this. You can see the statistics that how much amount histogram, that is frequency domain representative of the colors, that how much amount of color is present in the image. Okay. Then you can also perform operation on images, like if you load any image. Like this one, and you can just maybe transfer this image to 2. So this is the not of 1, so that is the negative of the image is shown over there. You can add these two images and see the effect. So it will be a completely white because you're adding 0 and 0. I mean the not an inverted image and the correct image, so you will get a complete whitewash. So what will happen when you add two images or XOR two images or perform the ANDing operation of two images? So this is what kind of results you will get that you can perform over here. And you can also do DCT, that is the comparison of the image. So you can see that this is the DCT matrix of the signal, and this is the quantization matrix. So if you if you increase the quantization factor, so you can see that this is the white image, that is okay. You have a black, you have all zeros frequency, the compression will be highest. But if you select something in the zones, so you can see that lower frequency are increasing, and as you decrease the quantization, you can see the frequency numbers are going to some extent. But if you increase the quantization matrix, you get more number of zeros to be included in the data packet, and that's how it does the compression. For example, we just load the same image. So if I click somewhere on the line, so you can see the allotment number of present over here. So this pixel will represent all these numbers of the frequency from the lower value to the higher frequency value. And as we know that the higher frequency value in the image, they don't have any much information about the image, so they can be removed by dividing with the quantization matrix and getting more number of zeros. So if I just increase the quantization matrix, so you can see that it will divide the lower frequency signals with the lower number and the higher frequency numbers with signals with the higher numbers. So hence we get more number of zeros, and which can be joined together in the data package to represent with the zeros, and hence we get the compressed image. And on the right hand side you can see the inverse of the DCT, and this is how the image will look like after recovery. So you have to decide that, okay, how much amount of compression you want and what kind of quality you want. If I increase the compression factor, so I get the gain space of 70%, but my image goes unrecognizable, so that may not be accepted by the user. So maybe till this extent I can accept the image, so I will get the 30% optimization of the image space taken. Okay, you can even see the original DCT value and the after quantization values. So you can quickly cover the concepts of DCT for your students. Okay. So this was a short and quick overview of the MentorDSP. So this is how you can cover, this is what you can help you to cover the DSP syllabus for your students. And even the students can make use of the software for learning about the DSP concept and practicing it well. Okay. So thank you very much for watching this video. Thank you.